So the most useful tool for solving exponential equations is, of course, the logarithm. We're going to have to talk a little bit about how they work before we can start using them. So the type of question I want to answer eventually is something like 2 to the exponent x equals 10. Now that would be easy if it were 2 to the x equals 4. So if we had that, right, 2 to what exponent equals 4? Well, 2 squared is 4, therefore x would be 2. It would also be easy if the question was 2 to the x equals 8, because 2 cubed is 8, so x would have to be 3. Would also be easy if 2 to the x was 16, because 2 to the power 4 is 16, so x would have to be 4. But when 2x is equal to 10, I have something between, like 10 is between 8 and 16. So this value for x has to be some number between 3 and 4. And it's going to be an irrational number. It's a horrendous, non-repeating decimal. So we're going to have to figure out how to make that work. But just based on this, I'm going to note that my answer to this question has to be a little bigger than 3, because 2 cubed is only 8. And it has to be less than 4, because 2 to the 4 would be too big. So I'm just going to jot that down. 3 is less than x is less than 4. So I'm just going to clean this up to make some space. You might have wondered why your calculator doesn't have a log base 2 button, or a log base 3 button, or even a generic log, so that you could use one button for many bases. And it turns out that there's a property of logarithms that you can exploit so that you don't need anything other than log base 10 or log base e, because it gets used in calculus so frequently. So I'm going to look at this number here, and the issue is that this 2 is, the 10 can't be written as base 2. That's an issue. But I'm wondering if I can write 2 as base 10. So what I'm going to try and pull off here is called a change of base. So execute. There's no J in execute. Execute a change of base. So what I'd like to know is if I can write 2 as some power of 10. I'm going to use an A up there. If I could do that, then I could replace this 2 with this power of 10, and then I could use log 10 as the logarithm of choice, and then this whole question just falls apart. So if I have this here, then this is just another exponential equation that I have to solve. So the variable is up here in the exponent of a 10. So you break a base 10 exponent by using a base 10 log. So I'm going to apply log base 10 onto this 10 to the exponent a. And if I do it on one side, I have to do it on the other. And so this log base 10 of 10 to the exponent a leaves me with just a. And over here, I have whatever log 10 of 2 is. So if I just grab the calculator here, log 2, 0.301 something 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 029996. So if you were to check that, what I've just worked out is that 2 can be replaced with 10 to the exponent 0.301029996. These numbers have exactly the same value. So what does that do for me? Well, I'm going to be able to take this equation, this is the one I started with, and I'm going to be able to replace this 2 with 10 to that exponent. So I'm going to do that over on this question, and then I'm going to erase this mess so I have some room. So instead of a 2, I'm going to write 10 to the exponent 0.3010299996 to the exponent x equals 10 to the 1. So all I did was take this equation here and I replaced the 2 with this awkward power of 10. I'm going to erase this as previously advertised so that I have some room. And then we'll discuss why this has helped you, even though it looks like it's made a catastrophic mess. Well, one of your exponent laws was that if you have something with an exponent raised to its own exponent, that you can just simplify that by multiplying those exponents together. So if you're not sure what I'm talking about, 2 cubed squared, well, that's 2 times 2 times 2 because of the 2 cubed, written twice. Well, that happens to be 2 to the 6, which I could have arrived at just by doing 3 times 2. So what I've got here then is 10 to the exponent 0.3010299996 to the exponent x is the same as this. And so if 10 to this exponent happens to equal 10 to the 1, then ipso facto, the only way this can be true is if this thing happens to be equal to 1. So if the exponent on this side is equal to the exponent on that side. So 0.3010299996x is equal to 1. Now to finish that, I just need to divide both sides by this horrendous number here. That's not new, that's just algebra skills. 301029996. This divides out that, and I'm left with x equals, and 1 divided by 0.3010299996 is 3.321. $928,095. Now that's encouraging, because back at the beginning of this problem I said I was looking for a number that was bigger than 3 and less than 4, and I got that. So what I've just figured out here is that this number, 2 to the exponent 3.321928095 equals 10. Now you've never been able to do that before, to get an exact answer. You would have always had to guess and check. But because I have these logarithms now, and I can use them to execute a change of base, I'm able to solve any exponential equation, like this one, no matter whether it's a perfect power of 2 or power of 3, etc. And there's no guessing and checking. I'm just flat out calculating it. So let's try a few more examples of that, just to make sure it makes sense. Let's try 3 to the exponent x equals 41. Now this is not a power of 3, and neither of these are a power of 10, but I'm still going to be able to use my log base 10 button to solve this as long as I do a change of base. So I'm going to start with that, change of base. I want to know if I can write 10 as an exponent of a equals 3. I want to know what a would have to be. So I'm going to use my log base 10. Log base 10 on 10a is log base 10 of 3. And because log base 10 is just log on your calculator, I'm not going to write that anymore. It's implied. Log base 10 on 10 undoes itself and leaves only the a behind. And log base 3, or log base 10 of 3, log base 10 of 3 is 0.477 12125. That's telling me that I can replace 3, right? I can replace 3 with 10 to that exponent. So if I do that in this equation, I end up with, instead of 3, I have 10 to the exponent 0.477121255 to the exponent x equals 41. I have a log base 10 now, so I'm going to use my I have an exponent base 10 now, so I'm going to use my log base 10 function on both sides of this equation. Log base 10 of 10 to the exponent 0.477121255x equals log base 10 of 41. So I'm going to have to move up here because I've sort of run out of space. But log base 10 acting on exponent base 10, those are antifunction pairs, so they undo each other. So all that's left on this side is this horrible decimal with the x attached. So 0.477121255x equals, and then I have log base 10 of 41. Well, I can just type that into the calculator. So I'm going to do that now. Log base 10 of 41 is 1.612 783857. There aren't any exponents left, and there aren't any logarithms left. I just have a number times x equals that. So I would finish that with normal algebra, divide both sides by this horrendous decimal. 121255 0.477121255, and I end up with x equals 1.612783857 divided by 0.477121255 is 3.38. 0.238.964. And if you were to check that, 3 to the exponent 3.380238.964 should give you 41 on the nose. And I can check that because 3 to the exponent 3 would be 27. That's not enough. 3 to the exponent 4 is 81. That's too big. So I'm expecting a number between 3 and 4, which is exactly what I have there. Now, looking at this example, there are a lot of numbers wiggling around on here. And we can shorten this up if we're a little tactical and a little unafraid of leaving symbols in our equations. This thing here, 0.477121255, that was just log base 10 of 3. So this thing here, I could just write it as 3 equals 10 to the exponent log 3. And then I could write that here as well. That's much faster. And then I could write it here as well, log 3. And just as a little bit of grammar, when you have an x multiplying a logarithm, it's good to write it in front so that you know that it's x times log 3 instead of log of 3x. So just to make sure that that x is outside of the function. Means that this thing here is just x log 3. And this thing was just log 3 log 3. And this was just log 41. So if I had looked at this equation, thought about doing a change of base, and then made all these replacements and carried them through, all I would have had to do to get this answer was log 41 divided by log 3. Well, I could have done that right at the beginning, just log of this divided by log of that. That's much faster. So I'm going to do one more example where we just shortcut that way. The log of this divided by the log of that, and then we'll go through the long process to see if we end up with matching answers. So for this one, 5 to the exponent x equals 32. I know that x has to be at least 2, because 5 squared would be 25, that's not big enough. But 5 cubed is 125, and that's too big. So I'm expecting an answer between 2 and 3. And this is a good habit to get into, especially with logarithms. If you can predict what the answer should look like approximately, then when you just randomly type things into your calculator, you have some sense of whether the answer that it spits out is correct. So 5 squared would not be enough. So this x has to be bigger than 2, and 5 cubed would be too big. So this x has to be less than 3. Now, just a minute ago, I said we could shortcut by taking the log of this thing and dividing it by the log of that. So if I were to just jot that down, log 32 divided by log 5. I'm going to type that into the machine, log 32. I'm going to turn it on first. Log 32 divided by log of 5 equals 2.153 38279. 2153 38279. Which happens to be a nice number between 2 and 3, as I was expecting. So we're going to go through the long process, and instead of rendering it as decimals, I'm just going to leave it as log 5 or log 32, whatever I need, so that we can track through to see if this structure shows up again. So I'm going to start by making my change of base. And I'm switching to base 10 because that's the only button I have. So I want to know if 5 can be written as 10 to some power. Well, I would use log base 10 to do that. Log of 5 equals log of 10 to the a by applying log to both sides. These undo each other, so that conversion factor is log 5. And are you noticing that that has happened 3 times now? That in order to write 5 as base 10, you would write 10 of log 5. If it was base 3, you'd write 10 of log 3. If it was base 17, you'd do 10 to log 17. This hasn't changed as we go through. So my next line in the equation then is, instead of writing 5, I'm going to write 10 to the exponent log 5. That's my conversion factor. To the exponent x equals 32. So I've executed my change of base. I'm going to apply log base 10 to both sides. And just for etiquette purposes, I'm writing the x in front so that I don't get confused where it is. If I do it on one side, I have to do it to both. Log base 10 and exponent base 10 are anti-functions. They undo each other. So I'm left with x log 5 equals log of 32. And the only thing left to do here is I have x multiplied by log 5. To break that, I divide both sides by log 5, and I'm left with this. Which is exactly what I had at the beginning when I started this entire exercise. So it turns out you can just hop straight to that if you'd like. And you notice that I just solved a base 5 exponential, and before a base 3 exponential and a base 2 exponential using only the log base 10 button, because these change of bases are so easy to execute. So that's why you don't have a generic log button. It's unnecessary. And 30 years ago, oh Lord, 40 years ago in the 80s, when pocket calculators were beginning to be a thing, programming a generic log would have taken an extra 3 or 4 circuit pathways in that machine, and it just wasn't necessary, because you could get away with it if you had any math skills to just do these change of bases. So there was no reason to program that particular function into the calculators, because it saved a little money, and you didn't really need it. So that's sort of a neat little technology legacy, right? Somebody made a decision based on how hard it was to build circuit boards 40 years ago, and the consequences of that have just propagated ever since. So we're going to take this and we're going to try a few more complicated versions or equations and see if we can handle that. So this question is asking if there is a number that I can park up there that would make 8x equal 14 to the x minus 3. So you run into a problem here. In order to break a base 8 exponential, you would need a base 8 logarithm. And in order to break a base 14 exponential, you would need a base 14 logarithm, unless I execute a change of base on both of these equations. So I'm going to do that, and I'm going to use 10, because log 10 is the button I have. Changing 8 into base 10, I would have to write that as 10 log 8. And to change a 14 to base 10, I would have to write 10 log 14. So I've replaced the 8 with this funny little structure, still to the exponent x. And I've changed the 14 to this funny structure, but there's still an exponent x minus 3. And they're still equal to each other. So I'm going to apply my log base 10 to both sides. So log base 10 acting on 10. It's lots of colors. It's exciting. X log 8 equals log base 10 applied to 10 to the x minus 3 multiplied by log 14. Notice again that I wrote this in front to make sure I understood it was x times log 8, not log of 8x. Now a log base 10 and an exponent base 10, you're going to get tired of me saying this, they undo each other because they're antifunction pairs. So all that's left then is x log 8 on this side and x minus 3 log 14 on this side. So those things are just numbers, and I'm down to a little bit of algebra here, so I'm going to have to do some distribution. I'm going to have to do some gathering like terms. So the first one I'm going to do, I'm going to make this say equals again. So I'm going to leave that alone, x log 8. If I distribute this log 14 into this bracket, I end up with x log 14 minus 3 log 14. I'm going to bring this to the other side, so we end up with x log 8 minus x log 14 equals minus 3 log 14. And there's an x in this and an x in that, so I can factor it out. I'm left with log 8 minus log 14. And if you're panicking right now because there are so many symbols up there, you could have typed this into your calculator. It's just a decimal, like 0.9 something. And you could have typed this into your calculator. It's just a decimal, 1.0 something. And then you could have subtracted them directly. I'm going to leave them there until the end so that I don't end up with rounding errors. But again, I've run out of space, so bringing this up here. In order to get this x by itself, I have x multiplied by this mass. The only way to break a multiplication is by division, so I'm going to divide both sides by this thing, which will leave me with x equals negative 3 log of 14 divided by log 8 minus log 14. And if I were to type that into the calculator, log 14 is 1.146 times negative 3 is negative 3.438384107, and log of 8 minus log of 14 is negative 0.243 0.38049. And so to finish that, I have to do this number divided by that number, and I would get negative 3.43438384107 divided by 0.243038.049 is 14.14. 1361. So according to our algebra here, 8 to this exponent should end up giving me the same value as 14 to this exponent minus 3. So I'm going to clear up some room, and I'm going to actually write that down and see what happens. So this number on an 8 in an exponent, 8 to the exponent 14.14751361 is 5.9769 times 10 to the 12. This is an enormous number. And if I take this same number and subtract 3, I end up with 11.14751361. And if I do 14 to the exponent, 11.14751361, I end up with 5.976926, if I round, times 10 to the 12. Notice that they match. So I was able to directly calculate this horrendous decimal that would make this side of the equation equal that side of the equation. And until you had this change of base skill, you weren't able to do that. So now that it's part of your toolkit, you can solve any exponential equation, whether it has x's on one side or both sides, just using log base 10 and your basic algebra skills.